Now that we know what voltage is, we can talk about capacitance, because we know that the definition of capacitance is the charge per voltage applied to a basically any structure that has two different conductors on it. So if we have conductor 1 and conductor 2, and there's some voltage applied across them, then this structure can be said to have a capacitance if we just look at how much charge builds up on these conductors. And as you might gather from this picture that I've drawn, this definition is general and it doesn't depend on the geometry of the capacitor in any way. But we also know, a definition for the voltage, in that it is the path integral of the electric field between 2 points. So then you could write the capacitance as the charge divided by this path integral definition of the voltage. Usually we do this so that A is the negative terminal and B is the positive terminal, so our voltage comes out positive. And if we do this, we can actually calculate the capacitance for something, because we can use Gauss's law to find the total charge on one of the conductors, like say the top one. And then you have all of the information that you need to find the capacitance of something. So the steps that we would go through to do this would be, first of all, find, first we would assume some surface charge density. And then we would find our electric flux density, usually using Gauss's law. An alternative way to do this first step would be to start by assuming a voltage. And then the second thing that we're going to have to do is find the total charge on one of the conductors. The third thing is, once we've found the electric field or the electric flux density, we can find the voltage using the electric field, which we can get from the electric flux density if that's what we found. And then last, we just put everything into our definition for capacitance. And the result should only depend on the geometry of the problem and the material properties. Any expressions you have for the electric field or for the surface charge density or whatever should cancel out of this equation. If they don't cancel, something is wrong and you should check. In class, I'm going to do an example about a parallel plate capacitor. I might as well do it here too. So let's say we have a capacitor. It has two conducting plates. It's a regular parallel plate capacitor. And on the top plate, we have some charge density, rho s. On the bottom plate, we have an equal and opposite charge density, which we know from the symmetry of the problem. So this is minus rho s over here. what we do is first, assuming that, let's say we know that the plates are large compared to the separation. So if they're separated by some distance d, that distance is small compared to the dimension of the plates. When that's true, you can say that the electric field between the plates is approximately the same as for an infinite charged sheet. And it's approximately 0 outside. So between the plates, the electric field starts on the positive charge and points down to the negative charge. And we have a contribution from the positively charged plate and from the negatively charged plate. So the total electric field is, let's define a direction. So that up in our picture is the z direction. So it is minus a hat z rho s over 2 epsilon naught from the upper plate and the same thing from the lower plate. Then we can use the Gauss's law to find enclosed charge. So we define a Gaussian surface that just encloses the upper plate of our capacitor. And really only the section from here to here contributes to the total charge that we're going to find. So when we do that, we're integrating, and here our surface normal vector is minus z directed. So we have minus a hat z rho s over epsilon naught, that's our electric field, dot minus a hat z dx dy over some area. Now none of these terms in the integral depend on x or y, so what we end up with is the area times rho s over epsilon naught is the total charge. Next, what's the voltage? The voltage is minus the integral from plate 1, which is A, to plate 2, which is B, of E dot dl. We're going to choose dl to be plus z directed, so we're going from the negative plate to the positive plate. So that's minus the integral from z equals 0 to h of minus a hat z rho s over epsilon naught dot a hat z dz. None of these things inside the integral depend on z, so we just end up multiplying by h. These two minus signs cancel each other out, and we end up with the voltage is equal to rho s h over epsilon naught. Then the capacitance is the charge divided by the voltage. Oh, up here, this is not true because the thing that I used in my electric field integral, that was E, not D. This epsilon naught should not be there. It should just be area times rho. Excuse me. Okay, so the capacitance is the charge divided by the voltage, which is area times the surface charge density here. I could only do this because the surface charge density was constant, because the plate separation is small enough compared to the plate area that it looks like an infinitely large charged sheet. If our problem didn't have that sort of symmetry or uniformity, the total charge on a plate might not be just the product of the plate area with the surface charge density, because the surface charge density wouldn't be constant. Anyway, that gets divided by surface charge density, H over epsilon naught, and we end up with, oh, that wasn't H before, it was D before. But anyway, we end up with epsilon naught A over H, or you can make it D, depending on what you named your plate separation variable at the beginning. I'd also like to talk about the stored energy in a capacitor. If we let W of t be the stored energy in a capacitor versus time as we charge it, we could also write that as the integral from 0 to some time t of the power. I'm going to use primed time coordinates for that. Power of time dt. Cool. And we know that power is equal to voltage times current, so we can also write that as the integral from 0 to t, voltage of time times current as a function of time. We also know that the current on a capacitor is just the capacitance times the time derivative of the voltage. So I can write this as leave the voltage part the same, and now it's multiplied by C dV dt. Note, these two are the same. So we're doing a time domain integral with respect to time, and then we also have a dV there. So we can rewrite this as move the capacitance out to the front, assuming the capacitance is constant with time, which it usually is. And then we have V of t dV. And that's nice. We end up at the end with 1/2 capacitance times voltage squared, evaluated from 0 to time t, whatever that time was. And that works out to 1/2 the capacitance v squared of time t, the ending time, plus whatever the starting stored energy was at time 0. So this is how much energy was stored in the capacitance over that time from 0 to t. This actually doesn't just apply to capacitors. If we have the stored, think about the stored energy in a parallel plate capacitor, which we just worked through. That stored energy is 1/2 epsilon A over D V squared, right? Because that's epsilon A over D is the capacitance in a parallel plate capacitor. But what if we divide the voltage by the plate separation? 1/2 V over D squared AD, because we ended up with an extra 1 over D there. Okay, this is the electric field. Well, the magnitude of the electric field. And this is the volume. What we're seeing here is that electric fields store energy in the volume in which they exist. So this is just a demonstration and not a proof, but in general, this works out to be true, that the stored electric energy in an electric field is 1/2 epsilon, material property, times the integral of the squared magnitude of the electric field over a volume that the electric field exists in. Electric fields can store energy. Cool.